this guy's giving me this headache. Okay. Studio. Copy. Report. Announcement. Bill counted. Not really. Announcement. Edit. Build content 15. Streaming lecture Wednesday. Okay, let me see. I post that. Paste. This. Region correlation 2. Okay, well, it's a correlation 2. So, let's see. Okay. Live, channel video, so that'll be live. Is this live? Okay, well, it's a correlation 2. So, let's see. Okay. Looks like this one is gonna work. Everything messed up totally. Alright. Now look at this. Oh man. Microphone works in here. One of the microphones, sure. don't give me any more stupid comment because I'm gonna blow. Give me any more comment that makes absolutely no sense or I'm gonna blow. Just shut up. There's something wrong with the it was just working fine, but all of a sudden there's something wrong with it. Any more comment that makes absolutely no sense or I'm gonna blow. There's something wrong with the it was just working fine, but all of a sudden okay, looks like I fixed it. Okay, that's a background noise. It picks up a lot of background noise. Okay, looks like I fixed it. How it's going? Background noise. It picks up a lot of background noise. Okay. It's a huge lag. It gives me the lag of maybe 10-15 seconds or more. Well, whoever is there watching, we're gonna be joining that in about an hour, about 52 minutes actually. This camera, okay. I can't see anything. All right. Okay, okay. All right. Go. Okay, I'm starting streaming now, Rita. Okay. Okay, folks, we're gonna start in about a couple of minutes. I'm gonna wait till more people show up so that we don't start too early. So that's about 3:30. Now, right now it's about 3:28. You can also adjust your own video settings in the bottom of the video window. On the right bottom corner you have the settings that's like looks like a little circle, and then you can make it with a little more resolution so you can see better. It's up to you, depending on whether you have a good internet connection. Okay. We are going over the lecture. This is lecture that's on the blackboard. You can find it. It's called Simple Linear Regression 3. Oh, looks like I call this Simple Linear Regression 2, which we are not going to do because we already done that, right? So we are going over the Simple Linear Regression 3, which is the topic that is on the blackboard. If you select the lectures and practice tests, there you will find that lecture as number 13, correlation 3. So that's what we are doing today. So I made a wrong name for the lecture, so I'm gonna have to change that. It says I call that 12 correlation 2, but it's actually going to be 13 correlation 3. I'm gonna change that name later, but right now it's not that important. What we're gonna be talking the title. What we're gonna be talking about is when you are having a scatter diagram, which you have seen for that quiz story. So you have something like this. You have a diagram, scatter diagram, where you have the the points representing x and y of the pairs that you have, and that could be something like this. And then you would say, And then you would say, okay, I see some trend. The trend looks like that. And what is the trend? And the question is, if you can put a line here so that this line would indicate the trend, where would that line be? Okay, so you can say, well, it has to go through middle like that. Now the question is, well, maybe not. Maybe it has to go this way. Right? So which one to choose? And you might also have some other, reasons to put it this way. So which one of those lines would be describing this trend that you cannot see the best? Okay, so that would be the topic of our lecture. So the one we're gonna choose is called least squared regression line. And it's also very often called simple linear regression line. And that would be, the way we're going to label it. So I guess in the future, I'm just going to use the uppercase letters. I'm going to say L, S, R, L. And that would, to me, means I'm talking about particular line here. So that particular line is not going to be an arbitrary line. So it's not going to be all three of those or whatever you can come up with. We have actually a particular way to do it. Okay? And let me describe to you that way. What is it? So let's say you have the trend like this. Okay? So now you could say maybe I get it here, maybe I get it here, maybe I get it here, maybe I get it here. Now where is that line? Okay? This is the idea. Any line you're going to put here, any line, something like this, you will have those points away from the line. So this point is here, is this much away from the line, this point is here, is this much away from the line, this point is here, is this much away from the line. So I'm talking about this distance, right? How much is that, right? You can measure it. You can find it out. Depending what the points are, right? You would have to know the equation of the line, you will have to know the x and y of this point, and then you can find it out. There is some sort of a story about Pythagoras theorem in the game and algebra and so on. We're not going there, so don't have to worry about that, but that's the way you would find it. And then you would have to do also the same thing for this point, and then you will have to do for this point here as well. Okay? Now that would be really difficult, because if we go for linear algebra, if you remember Pythagoras theorem, that would have to involve the distance between 2 points. That will have to involve a radical, square root. So that would complicate our business. It will be difficult. So we have a better approach. And our approach is going to be that we're going to calculate the vertical distances. This distance here. So this is not the distance from point to the line, because that would be the closest way to go to the line. It's vertical distance. Okay? And then this one here. And then this one here. Okay? And then, since you would be subtracting to find this distance, the y of this point and the y of this line, if you subtract y of the point, which is above, with y of the line, you get positive number. Now if you subtract y of the point here and y of the line, you get negative number, because this y is smaller than this y here. So that's a little bit of a problem. So you have something negative, something positive, so when you calculate distances like that. And you have to have a formula. It has to be, either y of the point minus y of the line, or y of the line minus y of the point. So you can't really have it both ways. To avoid that, we're just going to square it. And if you square it, it doesn't matter whether it's positive or negative. When you square it, it's always positive. So you square 2, you got 4. You square negative 2, you also got 4. So that's one trick we're going to use. So it's going to be a square of this distance. It's going to be a square of this distance, and it's going to be a square of this distance. And then you add them. So that's like sum of the squares. Okay? And it has to be small, because the line has to be close to the point. So if you choose another line like this one here, that will be a problem, because then you would have this point this much away, a lot, and then this point this much away, a lot, and then this point this much away, a lot. So then when you square that, you get much bigger squares. You get bigger squares in either case. So when you sum them all, you get even bigger. So this line would not be it. It is not a trend. But of course you know that, because you can clearly see that it doesn't really fit here. Well, this particular line does fit somehow. So again, I said before, you can maybe think maybe this line fits better. Okay? So we look here, what is the square of this plus square of this plus square of this for those both lines? Which one has it smaller? Smaller meaning the points are closer, vertically closer to the line. Okay? So now you can say, whoa, you know, I have to measure every single line you can come up with. No, actually, we have calculus methods that can decide which one is better. And more importantly, we actually know in calculus, and you will study that if you get to the calculus too, that there is one line only. And you will always be able to find it, which will have those squares, sum of those squares of those distances, the smallest possible, the best fitting line. There will always be a line like that. And there will always be only one. So you won't have two lines that will fit. There will only be one line that will fit. And there will always be such a line. So this is very important. Because of this calculus method, we know how to find it. Okay? So that is what we call least squares regression line. Okay? So there is such a line. All you have to know is what are the points. Okay? So, what do you know about lines, by the way? Okay? You know about lines, that lines are given with this kind of equation. You've probably seen that before. Okay? Maybe in a different way, in a different notation, but it's something like this. Okay? We have here x, which is a variable. It's an x of one point, x another point, x another point, so on. Y, which is also variable depending what an x is, so it's a thing you would be associating with an x. You have an x and y of the points around the line. This is called slope. That multiple of an x is called slope. And this thing here is called an intercept. So when x is equal 0, this disappears and y becomes this number. So that is on the y-axis where this line hits the y-axis. So I'm going to give you an example. So here I have the x and the y, and I have here 1, and I have this line. Okay? So what you know from algebra, I hope you do, I don't know, maybe you forgot that if you ever studied that, is that in this particular case, the slope of this line would be 2. And the reason is that if you move on to the right, you're going 2 up. That's how a slope is calculated. If you move on to the right, you're either going to go up or you're going to go down. That number, how much you're going to go up, is going to be the slope. Or if you go down, that number, how much you're going down, with sign that is negative, will be slope. So in this particular case, you are dealing with the 2 as a slope. Well, this particular thing here, where the line hits the y-axis is called intercept. So in this case it's 1. Okay? So you have the intercept and you have the slope. So once you have those two numbers, you know what the line is. Now I can calculate any point I want. Okay? If I want to find out what happens when x is equal to, all I have to do is to plug it in here. So I have a y equal 1 plus 2 times 2, and that is equal, of course, 5. And so on the line, I am hitting here 5 for a y. Okay? So all you need to do is to know, all you need to know about this line is what is this and what is this? What is the intercept? What is the slope? Once you know those two numbers, you know everything about that line. Okay? So that is our goal. Our goal is to find this line that is the best fitting line into the data, into those points you have on a scatter diagram. And to find this line, we need to know what is this guy, the intercept, and what is this guy, the slope. They're both numbers, so we need to know that. Of course, in case of variables, like we're talking about random variables in our story, we're not going to write y lowercase, we're just going to write an uppercase, because that's how we label the random variable. We'll label them uppercase, right? And the same thing for an x. We're going to label that uppercase. So that's the story about least square regression line. Again, this is the line that fits the scatter diagram. It should go close to those points. It should indicate the trend. The story is that it has to, when you are looking for vertical distance and square all of those vertical distances, you square the vertical distances, and then you sum all of those squares, it has to be the smallest possible. Of all of the possible lines you can have, that has to be the smallest possible. Okay? So now, how do you find the slope and the intercept? Okay, now, the kick is calculus. Right? If you study calculus 1 and you get to study calculus 2 and the calculus 3, I have to go to calculus 3. You will find how to find that. And it's really not that hard. This is one of the simpler topics in the calculus 3. Calculus 3 had many other harder stuff than that. So what I'm saying to you is we do that with calculus methods. But for you, you won't have to do any calculus methods. You're just going to have formula. Okay? And the formula, I know, they're not attractive, but you can have them. So you need the intercept formula, and you need the slope formula. Okay? The intercept formula is something that is pretty long. It's not an attractive one, but a slope formula is somewhat easier. And this is the slope formula. So I'm just copying that what you see in the lecture there. Slope formula is the one that is easier to work with. So you're gonna have to make a sum of all of the x, y's. You're gonna have to make the sum of all of the x's. Now you remember you already did that anyway, because you were calculating correlation coefficient. So there you have the x's, the y's, the xy's, the x squares, the y squares, and sum on the bottom of that table. So when you calculate the correlation coefficient, you need to have that table with all of the sum of x, y's, sum of the x's, sum of the y's, sum of the x squares, and sum of the y squared. So you already done that. So it's not something extra that you need to do. You're already supposed to have that. When you were calculating correlation coefficient, you already have it. Okay? That's how the top looks like. So you have the sum of x, y, multiply the number of pairs, sum of x's, sum of y's, you multiply these two and subtract from this first one. And on the bottom you have n times sum of the x squares. Again, maybe I put a parenthesis here so I don't get confused. And then you also have the sum of the x's to be squared and subtracted from this first part. All right? Okay, now you can say, wow, that's my slope. What about the intercept now? Well, we are going to use a little trick for the intercept. The trick is, again, the calculus business, is that this line that we call least square regression line, or sometimes simple least square regression line, or simple regression line, sometimes that way too, has to always pass through average. So when you have the scattered diagram with all those points, you're going to have the average of the x's, maybe here, okay? And then you're going to have the average of the y's, maybe here. So there is a point with the average. That point must be on this line. That's again calculus. So because of that, this must happen. So to find A, you need to know the average of y, the average of x's, which is not hard, and the slope, which you already calculated. And so the A is very simply y bar, the average of y, minus b x bar. So we have the formula for the intercept that is not hard to remember. So this is the formula for the slope, and this is the formula for the intercept. Okay. Now, there is another formula, so I suggest you go to the lecture, and that formula that you have in the lecture, I label it 1,5. So I actually label this one as formula 1,3. I label this one as formula 1,4, and I label the formula 1,5 that calculates that formula calculates the intercept by using summations. It's not an attractive formula, but for example, if you don't want to use this, you're going to use that one. One way or the other, you will get that intercept. Okay? So let me show you how is this calculated in one particular example. Now you do remember we have that quiz example. Okay? I'm not going to write the whole table there because we have already done that. That is the lecture of calculating R, which was the least correlation number 1 lecture. That's the one that we have before the test. Okay? We have a test on Monday. Oh, okay. So I wasn't teaching you yet the significance. All right. So, all right. So, but then we were calculating R in the lecture number 11. We calculated R. So when we were calculating the R, we had the whole table, the table with all of the x's, all of the y's, all of the xy's, all of the x squares, or all the y squares. I'm not going to reproduce the whole table, but I will just tell you what the bottom of that table was. So that was the da for the x's, for the y's, xy's, x squares, y squares in that table, and there is all sorts of stuff. But on the bottom we have a summation. So summation of all of the x's in that table, check the lecture, was 115. Summation of all of the y's were 133. Again, I'm talking about the example of 10 students taking the quiz number 1 and then taking the quiz number 2. So they have the scores, the x scores, which is the quiz number 1 scores, and then the y scores, which is the quiz number 2 scores. So the sum of all of the x scores is 115, sum of all of the y scores was 133, and then you multiply all of the x times respective y, and the sum of the old XY scores was 1795. Again, I know this is tedious, but that you already have done this, so you already have it. And sum of the X squares is 1653. And sum of all of the Y's was 2037. Okay? This is all you need. So now you have the story here. You have this formula. All you have to do is to plug it in. The B I'm going to write this a little over, a little later. So the B is M, 10 students, 10 pairs of quiz number 1 and quiz number 2 scores. Sum of X, Y, 1795. Minus sum of the X's multiplied with the sum of the Y's, that's 115 times 133. And now you have the downstairs N10 time sum of X squares right here, 1653, minus, and now you have sum of the X's squared. So make sure you understand that this is this number squared. So you need to have 115 squared, okay? So I have everything here in this little, well, not exactly little, but in this fraction. And all you have to do is to work out your calculator. It's not that difficult, using calculator, of course. And I come up with 0.8. I'm going to round that on 2 decimals. I got 0.80. Now there are more decimals there in the lecture. You check it out. I wrote that with, I don't know, like 9 decimals. I don't need that many, so I'm just going to keep 2 here. Okay, so now you have the slope. Okay, you still need the intercept. So this intercept has these 2 formula you could use. You could use that 1.5 that uses summation again, summations. You have all of the summations here, so you can use that. Or use a smarter idea, which was, I said already, that the line must pass through point that is average. Average of the score on the first quiz, average of the score on the second quiz. There you have X and Y, X bar and Y bar. That's a point on that scatter diagram somewhere there, and the line must go through it. So which means that A, like the same formula I was writing moments ago, and I call that formula 1.4 formula. So you have the A is equal to average of the Y minus B average of the X. Okay? So that's an easy business. What you have here is, well, it's going to be approximation, because obviously I have this approximation here, so I'm not going to be able to write exactly B, but more like approximation of B. But I have the average of the Y's. 133 is total of all of the Y's. There were 10 of them, so that's going to be 13.3. Okay, and now I have the B, 0.80, and the average of all of the X's. The X's are in this table that I didn't write completely, but down there is the sum of all of the X's, 115. There are 10 of them, so we have 11.5. Okay, now it doesn't take an Einstein to do the little calculation here, and you will get the slope, and I get a slope to be 4.06. Again, I'm using approximation with 2 decimals. Okay, So you got this intercept here. So now you know where the line is. Okay? So this is our line in this particular example when we have the 10 students taking quiz number 1, 10 students, the same 10 students taking quiz number 2, so they have score on both of them. You have the scatter diagram. You saw the scatter diagram is with some trend, and now you know what that trend is. The trend is this one, a line that would fit the data. Sometimes people call it best fitting line, but because there are different kinds of lines you can put in, we like to keep the more precise name. This one in particular is called least squares regression line. Okay, so you got actually the smallest, the least sum of all the squares that are vertically, the squares are vertical distances from the point to the line, blah, 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 blah. But in either case, we have the formula to find it. Okay? Now, you might ask the question, yeah, okay, now we have it. What the heck am I going to do with that line? Well, for one thing, you can plot it. And probably the idea would be to plot it in that graph that you have, the plot that you have points. But in either case, you can plot it. So the plot would go like this. So you have the 4.06. So this is my 1. I have 1, 2, 3, 4, 5. So 4.06 is somewhere here. So that's the intercept, and then you have a 0.8 times x, which means if I go 1 to the right, I go 0.8 up, so I'm about here. Okay? So now, so 1 to the right, 0.8 up. That's the idea of the slope always. 1 to the right, how much you're going up or down, the slope will tell you that, 0.8. Okay? So that's the line that you would put in that data. With all of those points, of course. So now, I'm going to show you that, of course, this is in the lecture. In the lecture, it looks like this. I'm not sure you see that. Yeah, it's a bad. Maybe I turn the light off. So you can see that better this way. Yeah, my monitor is. I hope you can see it now, right? So you have those points, and with those students, those are their scores on the first and the second quiz. So every point represents a student. And you can see this line here that I put in. That's exactly this line that we have, which is approximately 4.06 plus 0.8 times x. Okay? And you can probably agree that this line sort of fits this trend. You could probably say, okay, maybe I can have another line that will be maybe even better fitting this trend than this one that you see here, but that one would not be least square regression line. The least square regression line is only one, and we just found it. Okay, so least square regression line is always unique. No matter how many points you have, you will need to have, of course, at least 2. If you have 1 point only, that doesn't make any sense. First of all, it's not a sample, really. You have only 1 point, and a sample should be random. And which means you don't have anything random in that sample. You just have 2 numbers, so x and y, right? So you need to have at least 2 things. So as long as you have a 2 or 3 or 4 or more than that, you will have one line only, and it will always be one line, even if the data is not really with any trend. Such a line will exist. Okay. So I do want you to do the calculation for that example that we have a Boston Park, in which we have it's in the lecture, of course, in that story was we have certain number of police officers on duty for an X, and the same day we have a certain number of muggings. So was it week? I forgot already. Anyway, but that was the X was the number of police officer duty on a particular term, and then we have the number of muggings in the same term, time, right? And so we had that. We also calculated R there, and it was negative, of course, because the more police officers on duty, the lower number of muggings, meaning the negative correlation. We also calculated the significance, I believe, and we concluded significant. And you had a scatter diagram there as well. And if you calculate the least square regression line, you get something like this. And again, this I should say, this is in both cases just approximation. But if you calculate for the Boston Park example, you will get the intercept is going to be 9.798 approximately. And the slope is going to be negative because the line is going down. Whenever the line is going down, the slope is negative. When the line is going up, the slope is positive. So the slope is going to be negative 0.49 times x. So that's the Boston Park story. Okay? So again, when the line is going up, the slope will be positive. When the line is going down, the slope will be negative. That's worth remembering, of course. The line is going down. When x gets bigger, the y gets smaller. And so when x gets bigger, this number gets bigger. So you need to subtract it to get the whole thing, the y, smaller. Right? So it makes perfect sense. But again, if you look at this calculation, so you have to do that 1.3 for the slope, and then you calculate the intercept by using 1.4 or 1.5 formula. You'll get something like this. And the least square regression line in the Boston Park story looks like this. Okay, I hope you can see it. I should have put a wider angle camera, but again, you can find it in the lecture itself. So those are the points of the x and y, being x being number of police officers on duty and y being number of muggings, so that the trend is going down. The more officers, the less muggings, and the line really fits nicely the data. You can see the blue line, the least square regression line, indicates this trend. Okay, so now every time you do something in mathematics, right, you always have the question, why am I doing that? What's the point of doing this stuff? Yeah, I put this line into the data, so who cares? You know, I can put any line to the data. Well, what is this going to be of any worth to me? Well, the main point is forecast. Okay? First of all, you need to test significance. If your significance tests, which we did before the test number 2, tells you that there is a significant correlation. So which means that in that test you will reject the null hypothesis, and therefore you're concluding that you have a significant correlation. And both the quiz story and the Boston Park mugging story both test as significant correlation, right? So that was the story of the lecture number 12, tests of significance. Then this becomes a tool of your forecast. What does that mean? Well, it means this. Let me say I have a 11th student. In that group of students that I have, 10 of them were taking the quiz number 1 and quiz number 2. Maybe I have the student number 11. He took the quiz number 1 and he got on the quiz number 1 10 points. Now he's doing a makeup. He didn't take the quiz number 2 on time, so he has some excuse, so he's gonna do makeup. And we're gonna give him a makeup. Can you predict what is he going to score on a makeup? Now, if there is a significant correlation, you already know that there is a connection between X and Y, and you know what an X is. You should be able to predict Y. And you do exactly that. So this is the quiz story. This is the Boston Park story. So in this, we have the quiz number 1. So you use the first equation, and you can say I'm replacing X with 10. I have that information. You can say the student of mine, this guy on the quiz number 2 will score, likely score for him will be 12. I should actually use the precise probabilistic word. Expected score will be 12. Again, he does not have to score 12. He could score more or less or exactly 12. We don't know because it's not certain. But we expect him to score 12. Why? Because of the least square regression line that tells us so. Okay? We know there is the connection between X and Y. They are connected. We test significance of correlation, and our conclusion is that there is a significant correlation. We also know what the X is, his first score. So, plug it in. This is the relation between X and Y. Plug the X in, you get the Y. Okay? Or, let's say that I put 10 police officers on duty in Boston Park. In that time frame, that was the story in that Boston Park mugging problem story. So again, X is 10. We also know that in the Boston Park example, there is a significant negative correlation because we tested that. So the test of significance tells us there is a significant correlation. All right? We can say, we can predict the muggings, the number of muggings. Now this sounds like magic, right? But it isn't magic. We're just using this formula. We can say the expected number of muggings is going to be, I'm replacing X with 10. So I got 4.9 here to subtract with from 9.78, and I'm going to get, I'm not doing that exactly, approximately 5. If you put 10 police officers on duty, I am expecting 5 muggings. The stronger correlation is, the stronger that test is, which means you have that those tails and the the critical, the test value goes deeply into the tail there. That's a strong result. You will have conclusion that this is a strong correlation. So you will reject null hypothesis in just about any level of significance, which is the case in Boston Park story. If there is a strong correlation, then this is a good prediction. The stronger correlation is, the better prediction is. Okay? So you could predict. So people have a magic, people think it's a magical thing, I'm going to predict the number of burglaries in a particular area. Not necessarily any magic. We just have some other things that might have an impact some x that has an impact to that number of burglary, which might be y. And if we know what x is now, we can maybe figure out what the y will be. So this is very important. Now sometimes it's not important. Why do I care what this student is going to get? I'm just going to give him a quiz. He's going to find out something. He will, get some score on that quiz. I certainly would not be interested in predicting that. But sometimes you are interested in predicting that, and prediction becomes important tool for you. Right here. This is the tool for a prediction. Least square regression line. If you have it, you use it to predict. Okay? One thing you gotta remember, actually, there are two things you need to remember. You cannot use this tool in case you don't have a strong correlation. So if the tests of significance fails, meaning it's not gonna fail, it's gonna be, you do the test, but the test tells you, well, we don't really have enough evidence to conclude that there is a correlation, which means we don't have enough evidence to reject that no correlation thing that is a null hypothesis. In that case, you cannot use this tool. You will still have the line. The line will be calculated. The calculus says, yep, you're going to have it. The line will be again available to you. You find it, you get the equation, you can write that equation down, but you cannot use it as a prediction tool because you don't have a significant correlation. I mean, if I use the shoe size story, I already know the sizes of the shoes of the students have nothing to do with that second quiz score. So if somebody asks me, oh, here is the guy whose shoe size is 10. Can you tell me what's the second quiz score? I don't know. I can't use it. I would have a line, and I could actually even calculate using that line. But it would not matter, because the line would be horizontal. So I already told you that last time. Anytime you have non-correlated data, and the scattered diagram is just scattered completely without any trend, the line will turn out to be horizontal. So 1x, y, another x, the same y, another x, the same y, because the line is horizontal and y is always the same. In other words, this doesn't matter. What's going to happen is basically the slope is going to be close to 0, so you're going to get the first number always. If somebody asks you, what is the score on the second quiz of the guy whose shoe size is 10, what are you going to say? His expected score is 13.3. How do I know that? Well, that's the average on the second quiz. It's nothing to do with his shoe size. The average on the second quiz is 13.3. The average of those 10 students on the second quiz is 13.3. So you can say, I'm expecting his score to be 13.3 because I don't know anything better. But that's not a forecast. You're really making assumption that he's the average student. And it has nothing to do with his shoe size. Okay? So again, if the correlation is not significant, you cannot use this tool. The prediction cannot be done by using the least square regression line. No matter how you calculated it, you will always calculate that. It will turn out to be horizontal if there is no correlation, and you will not be able to make any prediction. So you should not try. Another thing, if the x is outside of the range of the data, you can't make predictions either. So for example, what if I put 30 police officers on duty? Well, when you take a look at that sample, nowhere in that sample we have a 30 police officers on duty, which means that your assumption about the number of police officers on duty, 30, is out of the range of your evidence of everything you have in that sample. We have there on the duty, I think, anywhere between 1 and 16 police officers. I already forgot. But yeah, anywhere between 1 and 16. So if I'm asking you what's going to happen if I put 30 police officers on duty, you can't make a prediction. You could probably say, oh, there's not going to be any migrants because there's going to be so much police over there. There won't be any mugging. By the way, if you put 30 here, you will get negative number here. You will be 9 point something minus 15 or something like that. It's going to be negative number. So you go, oh, that is going to be -5 number of muggings. That doesn't make any sense. You can't really use it. Again, if the data that you're interested in is outside of that range, you cannot make a prediction, right? Because the correlation is only in that range of the data you have, because that's where your sample is. You only have an evidence of that. Makes perfect sense when you think about it, right? So let's talk about it. In Chicago, there's lots of shooting there, right? Lots of shooting. So when you use the Chicago data about, you know, predicting how much shooting is going to be, let's say, this Friday, you can probably do that. There might be some X you can connect with that. But if I'm asking you how much shooting is going to be in New York or some other city, I don't know, let's take Miami, based on Chicago data, you cannot do that, right? Doesn't make any sense. Again, the same story here. If the X is outside of the range of the data, and our range of the data for police officers is between 1 and 16, or should I say 1 and 18, okay, I found it's 1 and 18, you cannot make a prediction outside of that range. So again, prediction cannot be done if there is no significant correlation, number one. Number two, predictions cannot be done if the X for which you're looking for expected Y, if the X is outside of the range of your evidence. Your data has X from something to something, that is where the correlation is significant. Anywhere outside of the data, you have no way of knowing whether that correlation stays that way. Okay? Also, I put in the lecture another thing here that is actually a connection between the least square regression line slope and the R, the correlation coefficient, and the connection is by a simple formula. Very interesting. If you know R, if you calculate R, this is a standard deviation, sample standard deviation of the Y's, so you can get that, sample standard deviation of the X's, you make a fraction, multiply R with that, and you get the slope. You would get this number slope. So you can say, oh, that's a simple formula to calculate. Well, not really, because you need to calculate the standard deviation, and that's plenty of calculation for standard deviation, right? So it's not really a simpler formula. So I should say stick to that 1.3, because that's a better formula to use, since you're going to have all of the summations done for calculating R anyway, so you get to use that one. It's smarter formula to use. Okay? We're going to make one Zoom session sometime soon, which I'm going to use to show you how to use your calculator to get the R and to get the least square regression line. So yeah, of course that's possible. You don't really have to do this nasty table calculation with lots of summations. There is something you can do in your calculator to get that. Okay, yeah. So we're gonna do a little Zoom session sometimes next week, instead of having a streaming session, in which I am going to show you how to use a calculator, because then I'll have my calculator to do that and share with you, right? So, but I'm not going to do that right now, because I would have to project the calculator on screen, or show you my calculator here in front of the camera, which is not a good idea in my view. Okay, so now we are done with the lecture today, which is number 13, least square regression line, or as I call it, correlation 3. I put the wrong title here on the stream. I'm going to change it. I'm going to edit and put the correct title. But that's the story. obviously, I really do expect you to read the lecture and to see a little more there in the lecture, because we have a little more calculations. You see the numbers properly, how they're calculated, in particular in the story about the police officer on duty. I really didn't do any calculation. They are just toss the least square regression line formula at you. So, and of course, I'm expecting you to work on the homework now, because now you have the correlation 2 homework, the one that is about least square regression line too. So you can work that one out. We are really done with the correlation business. So okay, so the next time we meet, we're gonna do a little Zoom session for me to show you how to use your graphing calculator, and we can talk about other things. You might have some questions about this stuff. And there is a lecture that is on the Blackboard. It's called correlation number 4. Okay, that lecture I am going to drop. That is a lecture about the Spearman rank coefficient, which is another coefficient that is used to indicate correlation, and it's a different calculation than the Karl Pearson correlation coefficient R that we use. So if you like to read that, but I will never ask you any questions about it, and it's just another correlation coefficient. Again, so there are different ideas how to calculate the correlation. That one is very good in case we have the correlation between the things that are going like down like that, or going down up like that, but they're not necessarily in terms of a line. They might be going down like curved. So that one is very good for that particular purpose, where Pearson correlation coefficient R would fail. So that is a lecture called correlation 4, but I am not going to ask you about it. So as far as correlation is concerned, we are done. So the next time we meet, Zoom session with a calculator. Make sure you have a calculator. We'll do that on Tuesday. No, excuse me, Monday. And then on Wednesday, and you can ask anything you want to ask. But some people want to ask something about the test, whatever that was gone already, or anything else you want to ask. You want to prepare any homework questions you have for me, so I can check your homework stuff if you're working on the homeworks. And then we're going further. We're gonna learn something new. Today also I got an indication from the administration that our end of the classes is gonna be May 21st or 22nd, depending what that is. We have sessions on Monday and Wednesday, so one of those 2 days is either Monday or Wednesday, so that's gonna be the last day of our classes. So either May 21st or May 22nd. Okay, that's what the college administration says. Okay, so I hope you understand what I was talking today, but then again, you can watch it over and over if you like. And again, work on your homework and over the weekend, so we can talk on Monday about the homework problems and the calculator use for the correlation, right? So I'm going to end the stream. Send me an email if you want to ask anything separately from what we were doing, okay?